Okay, so good morning and welcome to another Lisbon seminar. First of all, let me point out that I'm no longer one of the seminar's organizers. They now are organized by Valentina Loza and Liliana Apolinario. However, they were kind enough to let me present this last seminar about a very important work to me and to the OG LEAP group. Today, we have the pleasure to have a seminar by Felix Riehn. Felix did his PhD in Karlsruhe, Germany, working on the development of the cosmic ray hadronic interaction model CIBIL. He then came to do his postdoc in Lisbon some years ago, where he integrated the Lisbon OG group and worked on air shower phenomenology. Recently, he started sharing his research time between Lisbon and Santiago de Compostela. As probably you know, the OHECR collaboration has published for the first time results on the Muon air shower content fluctuations, and Felix has been the main driving force for this work. Together with the phenomenological works developed here at LEAP, this work sheds important light on the so-called Muon problem. Felix is going to tell us all about it today. So Felix, thanks for accepting this invitation, and you may start whenever you're ready.
Okay, thank you, Ruben. Yes, so I'm gonna, as you can see, and you all figured out already, I'm gonna talk about muons and trees at the same time. Yeah, so I was on FD shift last weekend, and somehow at 4 o'clock in the night this sounded really funny. But anyway, so you'll also learn what it means, what FD shift is. Okay, so what is this about? As Ruben already said, we have this measurement of the fluctuations of the number of muons, and that is the main result summarized in the plot basically here. And so the short summary is that there is no puzzle in the fluctuations. And so by the end of this seminar, hopefully, I hope at least that yeah, you will be able to understand this plot a little bit better. Okay, but starting from the beginning, 20 years ago, or even now a little bit more, this is what the spectrum of cosmic rays, and in particular the ultra high energy cosmic rays, look like, right? So you have this is the energy of these particles all the way to 10 to the 20 electron volts, and on this axis is the flux scaled by the energy. So that means that the spectrum or the flux is falling very steeply. So it just doesn't look like it because it's scaled up here, and then it falls even steeper towards the highest energies, and then there's this a bit of a puzzle. Namely, one experiment sees something like a suppression at the highest energies, while another one could say that it looks a little bit like it continues here. And why is this a bit puzzling? It's puzzling because we would expect, if the flux is all protons, we would expect that there is a suppression due to the interaction of the high energy protons at 10 to something 19 electron volts. That corresponds to center of mass energies with the CMD-B photons, where this falls directly on top of the delta resonance, so the cross section goes up a lot, and so all of these protons should lose energy through the interactions with the CMB. Or they're not protons, or interactions are different at the very highest energies. Who knows? That was the question, and that's why the Pierre Auger Observatory was built, to resolve the question how the ultra high energy cosmic ray flux, what it looks like. And the Pierre Auger Observatory, that's this thing that you see here. So we have on the left is one of our detector stations, which is basically a water tank with PMTs inside that measure then Cherenkov light as charged particles cross it. And then in the back, you see this building with these gray doors behind which there are fluorescence detectors The telescope is basically looking at the sky. And then there's lots of other infrastructure which is which we need to monitor the atmosphere, because our principal detector medium is the atmosphere above the array. And FD shift, by the way, means we're controlling at night these doors and these devices over here. It's quite fun. This is how it looks like at night. So this is why we're in Argentina. You can see here we're in the southern hemisphere. This is the large Magellanic Cloud and then the galaxy. So sorry. So we're in this high plateau in Argentina because of the clear air and darkness at night, because there's almost no people around. And yeah, you can see it looks very pristine. And okay, so on a more technical level, this is how it looks like as a whole. So we have this array of these water Cherenkov detector stations that I shown you, and each of the black dots here is one of these. These are 1600, around 1600 in total, and covering a huge area, so that we have a huge exposure to measure these low fluxes. And then there are 4 of these buildings that I also shown you with 6 telescopes, and here you see the field of view of each of these, which then overlook this whole array, so that we can take measurements at night what happens in the atmosphere above. And so this is only at night and when it's very dark. So that's roughly 50% of the time, while of course our water Cherenkov detectors take data basically all the time. So what is it that we're actually measuring? So we're not measuring the cosmic rays, but we're measuring what the cosmic rays do to the atmosphere. So as one of these particles comes in, and so in principle we could see photons, neutrinos, protons, neutrons, and nuclei. And so what I showed you, the spectrum, was for the charge part. So these are protons and nuclei, and this is what I'm going to talk about. But the same thing happens for all of them, and which is they have an interaction, and then new particles are produced, which have again lots of energy, which then can interact again, and you get what is called an extensive air shower, which are a bunch of charged particles in the atmosphere, which then will produce fluorescence light, which is what we observe with our fluorescence detector. This is the building I showed you. Here the doors are open, and you can actually see the mirror and the aperture inside. And yeah, actually now that I see it like this, I get a little bit of itching in the back of my neck, because this is exactly the situation you're supposed to avoid when you're on shift, is that during daytime the doors are open, because that's very bad for the telescopes. Because they're super sensitive, because of course, although these are very, very many particles that I've shown you here in the simulation, there's not much light coming out, so you need very sensitive telescopes. And then, okay, as this extensive air shower then hits the ground or reaches ground, or the particles in it reach the ground, then we detect them with our these stations of water Cherenkov detectors. Okay, and then so we have these 2 detectors, and then we have what is called a hybrid measurement. So here's a sketch of the array, these black dots, and then here's the field of views of our fluorescence detectors. As now I draw the shower just as a line. So as it traverses the volume above the array, let's say, there's energy deposited in the atmosphere, which in the form of light, which we see, and so we see this light going up and then going down. This is what we call the longitudinal profile, or the profile of the shower, which we measure then as a function of the depth in the atmosphere of the matter that was traversed. And so this is an energy deposit. So integrating this, we get and then correcting for things, we get the energy of the primary cosmic ray, or something that is very closely related to it. And then when we go to the ground particles, then we have close to the impact point, we get lots of signal, further away less. We get distribution as a function of the distance, and then we go to this like a reference distance. which we then calibrate with the measured energy from the fluorescence detector. Then it looks with a plot like this you do, and you fit it, and then you have a translation of what your signal at the ground means in terms of energy of the primary cosmic ray, and then you can apply that rule, that calibration, to the full data set of the 100% duty cycle data we take only with the surface detector array. So that's how we get to a huge exposure, and we avoid having problems with our energy assignment, and that is then the spectrum that we find. So you can see that there's lots of more features, like there's breaks and kinks, and there is definitely a suppression at the very highest energies. And okay, so this we can talk a lot about this. Now, what I want to say though is so the fact that we do see a suppression does not necessarily mean that we have protons, because all the nuclei can also dissociate and so on. So we are not sure yet. So what these particles are. So in order to figure that out, we can go back to our fluorescence measurement, or the measurement of the shower profile in the atmosphere. And so as I said, if we integrate this, we get something. We get the energy. If we look at the maximum of this profile, then we have something which is proportional to the mass of the primary cosmic ray. I mean, okay, this is fairly obvious. If you take a proton, it will have the first interaction somewhere given by the proton cross section. If you come with a nucleus, it has a different cross section, so that first interaction will be much higher in the atmosphere, and so therefore this maximum here also shifts, and then the shower also a little bit develops differently. In essence, you have something that is sensitive to the primary mass. And so if you look at that as a function of the energy, that's shown here on the left. So the average value of the maximum development of the showers in the atmosphere as a function of the energy, well, you get these points. Here on the right is the fluctuations of this quantity, and so if you compare these points then to the red lines or the blue lines, these are the expectations for pure protons in red and for pure iron primaries in blue. So you see we're somewhere in between proton and iron, which is also what one expects for realistic. Well, given the abundance of elements in the universe, that's what you expect is realistic for cosmic rays. And yeah, okay, so that's all good. However, there's a different way of measuring the mass of the cosmic rays, and that brings us to our muons. So on the left, you see this profile of the particles. Now, not the energy deposit, but the actual number of particles broken down into two different groups, muons and electrons. And so if you look for vertical showers, that's this line here. The ground at the Pierre Auger Observatory is roughly after 800 something grams. So you see you get lots of electrons and then some muons. And so all of these also change with regard to primary mass, but they change differently. And in order to get the mass, you would need them separately. But we can't get that from our surface detectors, or these water tanks. They are equally sensitive, more or less, to these two. So we can't distinguish them there. In order to distinguish them, we have to go to what is called inclined showers. Right? And this you see here. If you go to 60-degree showers, then the path through the atmosphere is longer. You're traversing something like, I don't know, 1500 grams. And so the electrons are attenuated very much, although there are still more than the muons. If you go to even more inclined, then finally you have only muons left. And so if you go to inclined showers, measure the energy with a fluorescence detector, you can construct this figure on the right, which has now, instead of just signal, it has the relative muon content in the showers versus the energy. And now that also depends on the mass, and that is what you see here. So on the left side, average number of muons in the showers, in relative units, in relative terms, divided by the energy, so that's more or less flat, the prediction for proton, for iron, and our data is, it's beyond iron, maybe barely compatible with pure iron within the systematic uncertainties. But it would be pure iron, and the slopes here does not look, I mean, it's more flat than the iron line here, right? So it can also not be pure iron, our data. So this looks a bit strange and hard to interpret. If you compare this, and so for this we go to 10 to the 19, could use any other energy, but we want that one. And we compare it there directly to the other measurement of the mass, and that's on the right, the plot. So on the x-axis is the average, sorry, not compared to the mass, compared to the mass measured with Xmax. So that's the depth in the atmosphere of the showers, where the maximum development is. So that's the number here, and on y is the logarithm of the number on the left. Okay, so you see our data is here, and then the predictions by the interaction models of our simulations are these lines here. Well, we're off the lines, so there's something wrong. We cannot interpret our data in terms of the primary mass of the particles, and that is what is referred to the Muon puzzle, because one could fix this by saying that we get the wrong number of muons in our simulations. And okay, so this is now the start. How do the air showers, or what goes into our observables? How are they sensitive to the primary interaction or the cosmic rays? So I want to talk about this in more detail. And so that for this, I have to talk about the air shower development. And so let's start with the start. We have a first interaction. So cosmic ray particle comes in, proton or a nucleus, and then there's going to be an interaction at hundreds of TeV, center of mass energy. So we haven't seen those in the lab, but we can assume that they're going to be hadronic because we start with hadrons in this case, but also something exotic might go on, right? So the interactions might be changed in some way. There might be chiral symmetry restoration, just to say one thing, or fireball produced. The other thing is that the secondaries that come out of this interaction will also have very high energies. And so apart from them being exotic particles, maybe, it could also be that the regular behavior of pions, kaons, and whatnot is modified. For example, maybe at these energies, there's no more Lorentz invariance. And so the secondary particles might be varied or change their behavior too. But what does an extensive air shower look like at these energies according to the standard model? So if we assume the first interaction is according to the standard model, we will produce hadrons, and these fall into groups. One group is neutral pions, photons, and electrons coming out of decays of hadrons. So why are these special? Well, because neutral pions decay almost instantly. So even at these energies, so the rest, let's say decay length is 25 nanometers, gamma factor of whatever, 1,000, still doesn't get you very far. So these decay into photons, and then we have high energy photons or electrons. And what do? Well, they either radiate, if they're electrons, radiate photon, Bremsstrahlung, or if they're photons, they undergo pair creation. And so what they do is they always produce other electromagnetic particles, photons or electrons. And so that's then an electromagnetic cascade, as this is referred to. And on the other side, you have charged pions, kaons, baryons, that have a relatively long decay length or long lifetime. So for pions, for example, it's 7 meters. That's without Lorentz boost. And so they will not decay before meeting the next particle to interact. So then you get a what's called a hadronic interaction, hadronic cascade, and that's basically the same thing as the first interaction happening again and again and again. So we have two cascades, the electromagnetic and the hadronic cascade. And so what happens with the primary energy? How is it distributed? So in the first interaction, in our two groups, the electromagnetic and the hadronic, the energy is split roughly like you see on the right. So 80% stays into what I call hadrons, which is baryons, kaons, and pions, charged pions. So the part that does not decay into electromagnetic particles, but interacts again hadronically. And then you have the electromagnetic particles, which take 20%. So that's after the first interaction. The second one we have already established is the same thing, just happens again. So you have an hadronic interaction. If again 80% of the energy stays in the hadrons, then you get that the energy in the hadronic side decreases with each step like this exponentially, and the energy on the right side, in the left side, sorry, electromagnetic cascade, increases exponentially. And so the energy flows from the hadronic side to the electromagnetic. And okay, so what does this mean for our observables? I've talked before about the position of the maximum. So the shower profile here, it's now broken down into muons, electrons, and photons. But this is the thing that we measure with the fluorescence detector. And so this is clearly dominated by the electromagnetic cascade, and if anything, then by the first few hadronic interactions, because you get a big chunk of energy coming from the first interaction into photons, and then these chunks get smaller and smaller because because of this regression. On the other side, the muons that we measure and ground, these come only at the final stages of this hadronic cascade, namely when the energy of the pions or of the mesons in general is low enough so that they have a chance to decay instead of interacting again. And so the muons are sensitive to the full hadronic cascade, so first interaction, second, third, until some larger generation when they decay, when the mesons decay. Okay, and so when you put this all together, this is roughly how it looks like, and the red here are the electromagnetic particles which are dominating. So now we can rephrase our muon puzzle. Again, this plot, Xmax, the maximal position of the shower profile in the atmosphere. So the electromagnetic cascade plus first few interactions. And here on Y, the number of muons at ground, which is the full hadronic cascade. So that's where our puzzle is in. And okay, I also said I was gonna talk about fluctuations, which I will talk about after this slide. So for this puzzle, if I go back one slide, so we have two scenarios now in order to increase this number of muons, because then if we go up here, then all is fine, then we can interpret our measurement consistently. And this is there's new physics going on in the first interaction. So that means in order to get more muons, we have to increase, that we have seen now, the energy that stays in the hadrons. And so we can do this by changing the first interaction a big chunk. So we produce, for example, many more kaons. That's what happens in this fireball scenario, for example, and or any kind of other exotic stuff. But because this exotic stuff is not seen at LHC or at lower energies in our labs, it has to be only at high energies. So we have to cram all of this into the high energy interactions. Second scenario is, it's called the standard physics scenario, is that we just so we have to introduce small changes in all the interactions, because so our muons come from the full cascade. So the first interaction, if we change our models there a little bit, but then also in all the others that follow, we still can get a big increase in the number in the end. So that's the second scenario. And so I also said I was going to talk about fluctuations, and this is how they enter. So I think it might have been, I hope it has gotten clear now that so the trees come in that in the sense that they do look like a little bit like air showers, except that the trees are of course the wrong side around. And so what do I mean with this, right? So we start with okay, we have the roots in the tree, and then there's a trunk, and then there's branching into different branches, then more branches, and then in the end you get the leaves. And so the leaves are our muons. If I go into one of these branches and rattle it, then some of the muons move, but not the others, or the leaves. If I go to the trunk and shake it, then the whole tree shakes. So it's clear the fluctuations that we see in the muons at ground, they are mostly dominated by fluctuations that you have in the first interaction. And then I also showed that it's the energy that you put into the different types of hadrons that is of importance. So if you, and the nominal fraction, let's say, was around 80% on average goes into the hadrons that keep the hadronic cascade. If I change that fraction, if that fraction fluctuates, then correspondingly the number of muons at ground fluctuates. Okay, so long story short, fluctuations are dominated by the first interaction, and let us look into our two scenarios. Okay, so now the measurement of the fluctuations. Yeah, this plot I've already shown. So we do this by taking these hybrid measurements of inclined showers, which have a long track through the atmosphere, so that that's how we get the muons. We have our energy measurement by integrating the profiles, and then basically we fit the average number of muons in this function to the data to get the average, and then our fluctuations are just scattered around this average. If you look carefully at this plot, you also see that so all our measurements have uncertainties. So in the energy, this uncertainty, as you see, is more or less always the same. And of course, this is our detector resolution for the fluorescence detector, and the same thing on the muon scale. Although here you see that it is large or visible at lower energies, and then at high energies it's very much reduced. So these resolutions, of course, we have to also subtract from this scatter, and then we have our shower fluctuations. And yeah, so that's basically what we do. Here I show you the total variance relative to this line in the previous plot, and then here are the resolutions. Flat energy resolution more or less, and then the surface detector resolution. Subtract these and we get physical fluctuations. Of course, there's many more details which make this a bit very, very hard, but I'll spare you these. You can look into all the papers if you're interested. So, and then we get the result, which is this. So on Y is the fluctuations versus the energy, our data, and then again versus the predictions by the interaction models, and you can see immediately these are within the range between proton and iron, and they also do compare really well with the composition that we get from the primary masses as we see them in the Xmax measurement, in the other mass measurement, and that is this gray band that is shown here. So for this, because the fluctuations, to get the fluctuations, we have to from the models we have to mix the composition as it is, and so what we do, so what is done for this is you assume, let's say, four different primaries. You make in this case iron, nitrogen, helium, and protons. You simulate all kinds of showers and try to describe the measurements that we have with Xmax. And then you find that you have to mix all of these showers with these fractions at 10 to the 19, and then you do that. So you have 60% nitrogen, 37% helium, and 3% protons. And with these numbers, you then can again calculate what you expect for the fluctuations, and that is this gray band for the three models. And yes, so we see that this gray band is compatible with, very well compatible with our measured fluctuations for the muons. And so if we now go back to our reference 10 to the 19, and then we can make this plot that I started with, which is we have our fluctuations here on the y-axis. That's the measurement at 10 to the 19, systematics and statistics. And then on x, we plot the average number of muon at that energy, also as we have measured it. And there we have slightly less statistical uncertainty, but a somewhat larger systematic uncertainty. And then we plot what we would expect first from the interaction models for any kind of mass scenario between. So if I go to this corner here, for example, this would be what, given this model, you expect to have in terms of fluctuations for protons, so they are large, and in terms of average number of muons for pure proton scenario. The pure iron scenario is down here, right? So we've seen the previous slide, low fluctuations in iron and large number of muons. And then of course the mixture to get from one to the other also can get you more larger fluctuations, because, well, the fluctuations depend on the distance between the averages as well as the individual pure fluctuations. And so this is if you're mixing proton and iron, then you're somewhere on this line. If you're mixing iron and nitrogen, then you're somewhere on this line. If you're mixing any of the four, you're somewhere in this contour. Okay, and then you have the region that is actually favored by the other mass measurement, which is the Xmax measurement. This is the star here for that particular model. For another model, it's here. For another model, it's here. Well, and now we see that in order to make these consistent, what we have to do is we just have to move the average number of muons to the right. Our fluctuations are fine. And that's what this plot summarizes. If I combine this with the other mixing measurements plot, which I showed you before, the one with the muon puzzle. So we have our shower profile measurement of the mass on the x-axis, the number of muons on the y-axis on this one plot. And then on the right, the plot that we just talked about, muon scale versus fluctuations in the muon scale. And now from the Aschau physics, we know that the muon scale is the full hadronic shower. Our fluctuations are mostly the first interaction. Xmax is the electromagnetic shower and the first hadronic interaction. And then here we have again the hadronic shower. And so in order to make this interpretation in terms of mass consistent, all we have to do is increase the hadronic shower, but we cannot increase or affect our first interaction, because if we would change that, then we would be running away from sorry, the data is here. Then our models would not correspond with our data here, and we would also get problems with the x-axis here, because we might be changing Xmax. So all we have to do is change, for example, for this orange model, 26% the number of muons, which corresponds to shifting plus 0.23 here, and then it's all good. Okay, so that brings me already to the conclusion. So that, as I said, we cannot change the first interaction too drastically. So the new physics scenario for the muon puzzle is not exactly dead, but it's not really needed, and the phase space for it is really limited because you can't violate these fluctuations. Although our precision in statistics is not super good. But it looks, the natural explanation is we just have to fine tune the models to describe the hadronic shower and move our models here within the range of the data. And well, I've also shown, I hope that that it's clear that the fluctuations are a good probe for high energy interactions and new physics. And so if we have more statistics, or even with that, so you should watch out for future maybe publications on let's say concrete limits on some of these exotic scenarios. And okay, so that brings me to the outlook. With the upgrade of the Auger detector, which is currently being deployed, and that you see in these pictures on the right, so adding radio antennas and these surface detectors, and scintillators on top of our stations, so that what we can do now is what I said we cannot do with the water tank of detector alone, which is separating muons from electromagnetic showers when we have vertical showers. So with this, we will be able to do it. Then we have a larger exposure, and we get more measurements of many more measurements of the muons. Or for the horizontal, we will get around the limited duty cycle of our fluorescence measurement, which only works in very dark nights, by using this radio, which works all day long to measure the energy, and then we have our muons from the inclined showers. And so this, for example, on the bottom left is a projection of after 10 years with these inclined showers with radio, how you would get enough statistic to make these small bins and very precise measurement of how the fluctuations really behave. And with that, it will presumably, hopefully, if there's also the mass ratios and so on work out nicely, we will be able to not only measure the average of the distribution of the number of muons, that's this plot here, and the width, but also, and this you see here, the tail that is present for protons, which comes from the production spectrum, of the actual production spectrum of the pions in the first interaction. And so then we will, by then latest, we will have a deep look into the first interaction and the physics there. Okay, thank you. That's already it.
Thank you, Felix, for this very nice presentation. Very, very clear. We have plenty of time for questions, so please just raise your hand or just speak up. It doesn't seem to have. Okay, so there's no question. I can make you a question, even though I mean this work. So what's your feeling with this Muon problem? So you're with this result, you're saying that it comes from the lower energies, right? So it's a problem with probably the low energy hadronic interaction models. What's your feeling? How can we tune this? What's the next step for tuning this? I mean, in your other life, you're also a model builder. So what are you thinking now? How to solve these problems? You have your mic off. Felix, mic.
Only Sophia heard me. That's yeah, no, that's too painful. I don't want to talk about it. No, so how it's a very tedious job, right? So this is a very unattractive scenario because, as you said it, we have to one has to look at there's not one measurement at LHC or at lower energies which we know if we describe that then it's done. No, you have to look at all of them and make your model agree to all of them, and then hopefully, I mean, then it might get better, right? Or we don't have the measurement yet that affects this, right? Because I mean, most of the interactions in the shower are pions interacting with nuclei, which we have hardly done in the lab, and certainly not at high energies. And so if there's just a I mean, there's also soft physics, right? So it's not like we have rigorous models to make clear predictions of what's going on there. So if we're off by a factor of 2 in one of the spectrums, nobody would be surprised. Or if we're missing some subtle effect, also nobody would be surprised, I would think.
Yeah, okay.
And, but yeah.
In any case, we don't need to have we would like to have a good enough description of the shower that allow us to trust on the composition results. And if you get that, then there's plenty of stuff that you can do and test, right? So, but I see your problem. The phase space is really big. Okay, one more chance. Any more questions to Felix?
I mean, if you insist at some next, I don't know, maybe next year or in 2 years, I can talk about the model stuff, which is yet another seminar. Right? That's
yeah.
Well, may I ask a question?
Yes, please, Elaine.
What do the other experiments say? So at lower energy, do they also measure the Muon excess?
That's it.
Yeah.
Very good question.
So that is yet another seminar one could give. So talking about, so I just picked out this one measurement that we just published now and that we were working on at LIP. But there are other observables or already in Auger which see this. There are other detectors. So there's the Argentinian groups, for example, they are very strong in burying detectors close to the surface detector stations, and then the ground absorbs the muons, the electromagnetic particles, right? So they have a very clean measurement of muons only, also for vertical showers. And these are at lower energies, and they also see this discrepancy. And then I think it was, I don't know when it was, in the 70s or something, it was already the first measurement, which now in hindsight we explain what we saw there, what was seen there is already this muon short deficit of the muons in the simulations. And it starts roughly at 10 to the 16 electron volts. That's yeah, there we have a measurement which shows the onset. And yeah, so there's an effort going on in combining all of these measurements and then trying to extract information from that. Yeah, I maybe could have had these plots in the backup.
It is not.
Sorry.
Yeah. No, I was going to say that it is not clear for me whether the results at LHC and forward could help to tune these models. You talk about this, but I did not get the point. So could this be useful or not to help the models?
Yes, but in a less direct way than probably what you maybe think of. So the energies here for the first interaction are much higher than at LHC.
Yeah, for sure. This is for sure.
140 TeV or so. However, so it helps to improve the extrapolation error, right? We do have to make extrapolation, but if we tune only to temperature data, let's say, which is at below TeV, then the extrapolation is even further. And so in that sense, LHC helps. And of course, if they with a larger acceptance, right? So there were not so many dedicated forward experiments at other accelerators. So that's also a plus. We don't have, in other words, we don't have in this high energy regime, we don't have much full phase space coverage, and LHC is the best
Mhm.
in that respect.
There is also an effort for producing a proton oxygen and an oxygen run.
Yes.
I think that, and this will be also very helpful for us. So, but I think there will be in the future a seminar at LEAP about
and
this.
Are you participating in the discussions? Because it is not clear if we are going to have this proton oxygen in the future. It is under discussion.
Yes.
But are you from Auger? Are you making an effort to have these collisions or not? Or are you expecting that the heavy ion community provides this?
No. There's this. There was recently a workshop about this, and there were also people from Auger presenting their results. And
yes.
So it's not going to be done, I think, if there is not interest from different sectors. So from the heavy ion people, from the cosmic ray, from the from the light system. So, but I think it's progressing well.
Good.
Okay. Last question for Felix. Any? If not, okay, Felix. Once again, thank you very much for this very nice seminar. Thank you all for being here today, and see you next week. Bye.